So welcome to the second half of the video on Darcys Law as part of the Fluid Earth Dynamics course. And the structure that we were talking about last time was porous flow through a medium composed, for example, of fine grains. It could be water flowing through fine grains. And we looked at the structure of that material. We said we would approximate the structure as a series of pipes, and that we'd look at individual channels, and we'd consider each individual channel to be a pipe. And from that structure, we build up a simplified three-dimensional network made up of cubes, each cube having a dimension B on each side. So this is just like mineralogy, and giving a full structure that looks like this network shown here. Back in 3 dimensions, you can think of a series of these pipes making up, or of these unit cells making up the full object. Okay, and we're going to worry about flow through each pipe. Each pipe is spaced from the next pipe by a distance b, and each pipe has a radius r. So that's the structure we're looking at, and we're going to try to continue the analysis that we started in that structure. And this is the structure that we looked at. The pipe flow problem is given a special name, and you can ask Professor Tesse exactly how to pronounce it, but it's pronounced approximately Poisson flow. So it's flow through a pipe as shown in this slide. So there's the pipe. It's set up in cylindrical coordinates with r, theta, and z. The fluid is flowing in the z direction, right? So it's flowing that way. And it doesn't have any components of velocity in the r or the theta direction. Okay, so that's the problem we began to set up last time. I'm going to switch back to the notepad. And we had it set up that we had an expression that we arrived at last time, that the pressure gradient, dP dz, is equal to the viscosity divided by the radial position inside the tube times the derivative with respect to r of r times the derivative of the velocity with respect to r. So again, it's the velocity in the z direction, and the pressure gradient is a pressure gradient in the z direction. And this pressure gradient, I'll remind you, we always treat as being constant. So it's for a constant, steady flow, no acceleration in the fluid. It's flowing at a steady rate. What arrives at one point arrives at the next point later on. So this is Stokes' equation set up in particular now for cylindrical coordinates. So if we're talking about flow through a pipe, here's our pipe, there's our velocity gradient, looks like that. And so it has the maximum velocity in the center, so Vmax in the z direction is there. And the boundary conditions are going to be, as you'll see in a moment, if we call this r equal to 0 in the center of the pipe, here's the radius of the part. The outer radius is r equals some large value, or some large r. And the velocity out here, if we have no slip boundary conditions, the velocity at little r equal to big R is equal to 0. So those would be our 2 boundary conditions, that we have a maximum velocity in the center and a 0 velocity at the outside. All right, to make progress with this equation, now we need to integrate twice. All right. So we have basically the second derivative of the velocity is equal to a constant. We're going to integrate twice, apply our boundary conditions, and come up with an expression for the velocity as a function of radial position. So what I'm after is I want to know the velocity in the z direction as a function of radius. What is it at the center? What is it at that point? What is it at that point? Okay. So the r vector runs, you could think about it as running in that direction. Okay, so we're going to take this r, bring it to the other side of the equation. dP dz is constant, so we can take it out of the integral. And so we're going to have the integral of r dr. All right, we're going to take this r dr, move it to the other side of the equation. And we're left with mu times the integral of the derivative of r, derivative of velocity in the z direction with respect to r. And we can integrate that. It's 1/2 the pressure gradient, dP dr, times r squared. That's equal to the viscosity times the bit that's inside here, so it's times r, the velocity gradient, And then we need to add on some constant C1, our integration constant. Okay. So what I'm going to do is I'm going to multiply this whole thing, this whole equation, both sides, by 1 over r, and take it to the next step. All right, so the second integration, I have a half times dp dz, pressure gradient, times integral of r dr is equal to mu times integral of dv z, which is a function of r, plus the integral of c1 over r. All right, dr. So that's what I have to integrate, and if I do that, I end up with 1/4 times the pressure gradient, dp dz, times r squared, plus mu, is equal to mu, the viscosity, times the velocity in the z direction, which depends upon where you are radially in the tube, plus c1 times the natural log of r, plus some second integration constant C2. And the boundary conditions, again, that we had, the BCs, the boundary conditions are that velocity of z at r equal to 0 is equal to v z max, whatever the maximum velocity is. So that's at r equal to 0. And the second boundary condition is that v z, when little r is equal to capital R, that is at the edge of the tube, is equal to 0. All right, so those are the boundary conditions. I can use those two boundary conditions to solve my two integration constants C1 and C2. Okay, so first at little r equal 0, I have 0 is equal to mu times, all right, so I'm going back up to this equation. I'm solving it at little r equals 0. That goes away. So I have mu times v, the velocity at the center of the chamber, which I said was v max. All right, so it's this boundary condition, plus c1 times the log of 0, plus c2. Okay, and if you quickly think back to when you learned about logs, you hopefully will remember that the log of 0 goes to negative infinity, right? So that has a problem. We can't allow the velocity to go to infinity, and so that tells us right away that we should set c1 equal to 0. Right, if we set c1 equal to 0, this term goes away, and we don't have to worry about the fact that the log of a very small number gets to be huge, because we can't allow infinite velocities in our systems. So that gives us the first constant, c1. And we do that because we have to keep the velocity finite, so we set c1 equal to 0. All right, and now we apply our second boundary condition. So at r equal to capital R, velocity in the z direction is equal to 0. And that implies, we plug that back in, that C2 must equal minus 1/4 pressure gradient times R squared.
Can you bring it down a little?
Okay, so that's the expression for C2. We get it from our second boundary condition. So this is the boundary condition that we applied. And so we can plug that back into our velocity expression, and we have the velocity in the z direction as a function of radial position, right, is equal to 1/4, 1/4, times the viscosity times the pressure gradient, dp dz, times r squared, little r squared minus capital R squared. Okay, and okay, so that's what the velocity looks like. It says the velocity depends upon where you are in the channel. If I'm at the center of the channel, little r is equal to 0, and I get my maximum velocity. And if we're at the outside edge of the channel, little r is equal to big R. They subtract from each other, and I get 0. So a couple things for you to think about is make sure this whole expression is dimensionally correct. So go through and check that pressures cancel out and distances cancel out to give me a velocity. And then I can write Vmax, the velocity in the center of the channel. So this is at little r equal to 0, is equal to minus r squared divided by 4 times the viscosity times the pressure gradient. And you might look at this and be saying, all right, professor has fallen asleep. He's got a sign problem because you can't have negative velocities. We're only going to have velocities flowing downstream. But you want to remember that dP to z, the pressure gradient, is negative. So the pressure gradients are always less than 0 because flow goes downhill. And so that pressure gradient, as we talked about previously, has to be negative. Okay, so what we want to do now is we want to calculate the flux of material, or the volumetric flow of the material. And you remember from when we talked about this problem in terms of channel flow, we calculated the volumetric flow or volumetric flow rate. We wrote it as big Q, and that's like going down to the end of the Mississippi with your bucket, and you collect water or fluid coming out of the Mississippi, and you can see how much fluid you get, how many gallons of fluid, how much volume per unit time. Right? And the way we did that is we used the mean velocity, and we calculated the mean velocity integrated over the area. All right, so we're going to calculate the integral from 0 to r. We'll look at this in more detail in just a second. And 0 to 2 pi of the velocity in the z direction, which is a function of r, times r d theta dz. Okay, so let me go back to the overheads, the PowerPoint, for just a minute. And we can look at this problem just to remind you of where we're at. Okay, so here I'm back in my channel flow, or my pipe flow. I have flow coming out this pipe, and I have a velocity gradient shown here. So there's the velocity gradient. It's maximum at the center, 0 at the edges, maximum here. And now I want to do is calculate the flux coming out. And so I need not just the velocity, because the velocity is a function of position, but I need the mean velocity of the fluid coming out. So I integrate, and I'm going to integrate that over the cross-sectional area. Okay, and so I have to integrate over this area on the outside. And the way I can think about that is I have to integrate along the radial position, because the velocity is a function of radius, right? As shown here, the velocity has this profile. And so the velocity depends upon r, and then I have to integrate it across the full area. And so the way you can set up this problem, if I can go back to my notes, I'm going to think about fluid coming out this pipe. So here's the end of the pipe, and it has some radius going out, and I can think about taking a ring, an annulus, here, and I have to integrate around theta. So this is my angle theta, so I have to integrate from theta from 0 to 2 pi. Takes me around here. That'll give me the area of this annulus. And then I have to integrate those annuluses from the center all the way out to the edge. Okay, so that's the reason for doing an integral over theta, to get the area of the annulus, and then once I have the area of the annulus, I can integrate that over the full area of the pipe. What we need to do now is we need to integrate over the area of the cross-sectional area of the end of the tube. So it's the integral of velocity as a function of r. And if we integrate, we're going to integrate from r equals 0 to big R. And if we do the integral over theta, it gives us 2 pi. So we're going to get 2 pi out from doing the integral from 0 to 2 pi of d theta. And now we're left with an integral over the rest of the cross-sectional area. Okay, so the area of the annulus is 2 pi times r dr. And now we have to integrate that out over r. Okay, and if we do that, when we plug our velocity term back in, velocity as a function of r look like 1 over 4 times the viscosity times the pressure gradient times little r squared minus big R squared. Plug that in, we do the integral for q, and we end up integrating q of z is equal to 2 pi over 4 times viscosity times the pressure gradient. The integral from 0 to r, a little r cubed. All right, we have r squared here and another r up there, minus little r times r, big R squared dr. And if I do that, I end up with pi over twice times the viscosity times the pressure gradient, dp dz, which is driving the flow, times r to the 4th over 4 minus r squared over 2 times big R squared. And I have to evaluate that between 0 and big R. Okay, so that's what we have to do. That's all pretty straightforward. And if we plug and chug for a minute, we end up with the flux in the z direction, or the discharge in the z direction is equal to minus pi r to the 4th over 8 times the viscosity times the pressure gradient. Okay, so that's the volume of fluid per unit time that's being discharged through our through our pipe. And we can convert that into what is a flux by just taking big Q and dividing it by the area. And the flux always has units of volume per unit time per unit area. Okay. And so the velocity in the pipe in the z direction, the mean velocity, is just equal to the flux in the pipe in the z direction. It's just equal to minus r squared over 8 times the viscosity times the pressure gradient. Okay, so this is for a single pipe. And now we have to do is we have to go back and look at our porous medium, which has a more complex structure. It's made up of a lot of pipes, and we have to take into account that we're flowing through a lot of pipes and worry about what fraction of the material that we're flowing through is pipe and what fraction is solid grains. All right, if I can go back to the screen for the PowerPoint for just a minute. So this again is our geometry, and we're going to do a bunch of math, and we're going to end up with Darcys Law, which is shown here. Okay, so now I need to worry about this structure that I have a lot of pipes coming out of this front surface that's facing out toward you. And I need to account for the fact that all I'm doing is flowing through those pipes and not through the whole area. So I just need to do some simple normalization to take into account the fact that I only flow through the pipes, I only flow through these blue parts, and I don't flow through the gray part. Right? So I have to do some area normalization to get that problem taken, or that point taken into account. Okay, so we're going to make the medium now, rather than one pipe, we're going to make it a porous medium. We're going to make it sand with water flowing through the sand, but in a very special geometry. Okay. So we have the mean velocity for each pipe, and what we need to know next is what's the area fraction of pipe. Right? And I always think this is a problem like you do in mineralogy. You calculate unit cells and how many atoms are in a unit cell. And so we have kind of a situation where we just look at the end face, we have Here are 4 of the pipes that we have that are flowing fluid out toward you. And they sit on this cubic network of side B, side B, side B. And the radius of this pipe is R. And so I want to ask, what fraction of the surface is actually pipe? Then I want to look at the area channels, or the area of the pipe, normalized by the total area. And then I'll know what space I have available for transporting fluid. And that's just equal to pi r squared is the area of a pipe, and then I have to normalize it by b squared. And this is where you have to, again, think about what you learned in mineralogy. You have 4 pipes, but each pipe is shared by 4 different grains. So this pipe only belongs 1/4 to this area, and you get another quarter here, another quarter there, and another quarter there. And so you get 1 pipe per b squared. So that's the area fraction of pipe. And so the Darcy velocity, which is the fluid coming through the whole medium, not through one pipe, but through the whole medium, is the mean velocity is just equal to the weighted fraction. I'm going to weight by the cross-sectional area, pi r squared times divided by b squared. And I'm going to multiply that by my mean pipe velocity. And that's just equal to pi r squared over b squared times this mean pipe velocity, which was, you look back in your notes, was r squared divided by 8 times the viscosity of the fluid times the pressure gradient. And if I put all that together, I end up with minus pi over 8 r squared, radius of the pipe, over b squared, the size of the unit cell, times the pressure gradient. Okay, so we're almost home. We have the expression for the Darcy velocity. And what we want to do is to, rather than relate it to the size of the pipe, we'd like to make it kind of independent of pipe size and talk about it, this expression, in terms of the porosity of the system. So I'm just going to make one more sort of geometrical argument to change this expression and write it in terms of porosity. So what I want to do is I want to talk about the same Darcy flow, but I want to look at it in terms of what I'll call the porosity, which I'll call phi, which is just equal to the velocity of pores, or not the velocity, the volume of pores, divided by the volume of the cube, or of our sample. All right? All right, and the volume of the pores is going to be easy to calculate. The denominator we can get right away. It's just b cubed. So I did it for one of our unit cell cubes. And now, if I can go back and look at the overhead PowerPoint just one more time, we're going to look at one cube, such as the one shown here. And we want to calculate what fraction of that cube is actually occupied by blue lines and what fraction is occupied by blue lines. So you can see that there are 12 lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 12 of those pipes. So I need a 12 up here. But we've already seen that you only get, each pipe is only 1/4 in the unit cell. So this is the number of pipes. This is the fraction in our cell. And then I have to multiply it by the volume of one pipe, and the volume of one pipe is just pi r squared, that's the cross-sectional area, times its length b. Okay, and that's, you grind it out, it's just 3 pi r squared times b, and that's divided by b cubed. Okay, and so I can plug that back in to our Darcy velocity. Mean velocity for Darcy divided by, or in the z direction, is just equal to minus pi over 8 r squared, r to the fourth over b to the fourth, b squared over mu times pressure gradient. And I can rewrite that in terms of this expression for phi, the porosity of the system. So phi is called porosity. It's the fraction of the system that's actually pores. And so in terms of porosity, this just comes out looking like minus phi squared, the porosity squared, times the size of the cell squared over 72 pi, times 1 over the viscosity times the pressure gradient. All right, so that's the Darcy velocity for a very special geometry. And we'll look at other geometries in class. But that's for the case where we have this cubic network of pipes connected to each other. And so this is often written in the form minus 1 or minus k, the permeability, divided by the fluid viscosity times the pressure gradient.
Can you bring it up?
And so this piece here, phi squared, b squared over 72 pi, is kind of a geometrical term. It depends upon the details of the pore structure that we assumed. And that all gets lumped into this term, the porosity of the system. Okay, let me return to the PowerPoint for just a second so I can conclude. So this is what we just derived. Again, it's for a very special geometry. This expression for the Darcy velocity or the Darcy flux is just given by the permeability K divided by 1 over the viscosity times the pressure gradient. Okay, and so you can see the velocity, and I would remind you that one could write this as just equal to this small q, the flux, that the flux is given by the pressure gradient. So the pressure gradient drives the system. So this is what makes the flow happen. It's depends upon viscosity. As the fluid becomes very viscous, the flow goes slower and slower. So as mu becomes a large number, it's in the denominator. If mu becomes large, the velocity slows down. And K tells you something about the pore structure. And so as K gets large, it means you have more and more pores and the velocity goes up. So it has kind of the right physical sense to it that you can see that the parameter dependence is all, I think, consistent with what you might expect. So let me stop there for today. Thank you.